Righto, this is the second part of the differentiation video. It's preceded by sort of a bit of theory and a few um, important facts and so on for differentiation. So now I'm going to work through a load of worked examples. These are taken from Save My Exams, excellent resource. And Very good value for money should you choose to sign up to it. Okay, so we're going to go through all the various techniques and things that we saw in the first video. Right. First question. Find the x-coordinate of the stationary point on the curve y equals 2 minus root 3 x squared plus x minus 1, giving your answer in this form. A and B are rational numbers. Okay, stationary point, I might not have spelt that out, but basically where we've got a curve, maybe it does that. Stationary sort of means that it's not going up or or down. It's that moment there. It's the sort of as x increases, it's where the curve turns basically. Stationary points are also called turning points, which are perhaps a more meaningful name. So stationary points, turning points, you might see either of those. So it's essentially where the curve is, or the tangent to the curve is horizontal. So the gradient at that point is zero. Okay, so let's have a look. Anyway, first thing we need is the derivative. So this is the gradient function, as I've called it. And at the stationary point, as I've just said, the gradient is going to be zero because it's going to be either a maximum or a minimum like that. Okay, so knowing that, then we can form this equation. This is just an equation in x, and basically when we solve that, we're just going to get this. All right, bit of rearrangement. Now this has got an irrational denominator, um, and we do need to get it into this form, so we need to rationalize the denominator. I won't go into the details of that, just to say that as a reminder, the way we would do that is multiply the denominator by the conjugate of this irrational number here, and the conjugate being 2 plus root 3. I have to do the same to the numerator, of course, work that through, and then we get this. So that is the answer. That is the x-coordinate of the stationary point for this. You're not actually asked whether or not this is a maximum or a minimum, so just a little bit of extra information on this. When we consider what this number is here, well, root 3 is less than 2. It would be, wouldn't it? Because root 4 is 2, so root 3 is going to be less than 2. So this is a positive number. So this quadratic is actually a positive quadratic. If it's a positive quadratic, it's going to be that shape. And therefore, the turning point here is going to be a minimum. Okay, so that is one. All right, we've got plenty more examples to go through. The radius of a circle is increasing at the rate of 5 centimeters per second. Okay, so find in terms of pi the rate at which the area of the circle is increasing when r equals 3. Yeah, okay. So anyway, we're told the rate of increases 5 centimeters per second. So this is telling us that if r is our radius, yeah, then dr dt, that's the rate of change of the radius with respect to time, is equal to 5. Um, Now, of course, we've not just got these two variables in this problem. We've also got the area, which is we know to be pi r squared. Um, so if we can imagine the radius increasing, then we're going to have as the radius increases, we've got the area increasing, and at what with rate with respect to r, then that is the derivative of a with respect to r, which is 2 pi r. Right, okay. So, um, okay, we are wanting the rate at which, the rate at which the area is increasing with respect to time. And this actually is equal to this product here. Now, this comes out of the chain rule, and when we're thinking about how we differentiate composite functions, then this is more or less the same concept. dA dr is equal to times dr dt, beg your pardon, is equal to dA dt. And now it looks a little bit of a sleight of hand, doesn't it, to do this? But in actual fact, it's all real. I mean, these are real things. And that dr is the same as that dr. These are all functions, of course, but functions of x, of t, beg your pardon. So we can do this. So it's like a bit of reverse cancellation, isn't it? Anyway, so the point being, of course, we know this, and we know this. The ADR is 2 pi r. The RDT is that. So therefore, the rate of change of the area with respect to time is going to be equal to that. And then for when r is equal to 3, we can evaluate that, and it comes out at 30 pi. All right, so this chain rule thing here is very important. I mentioned it in the first video that it crops up, and here is an example where we're actually doing that. We're actually forming a derivative from two other derivatives that we know. Okay. Right, good. Okay, let's move on. Given that y equals this product, show that dy dx, the derivative, is equal to this lot here, where a, b, and c are integers. Okay, so well, if we rewrite this as this, it's generally more convenient. Well, it's always more convenient, to be honest, to express it with an exponent, because we use that exponent, don't we, when we're differentiating an algebraic function. So, and what we have to do here now is we've got a product of two functions. Um, so we're going to use the product rule for taking that as our f and that as our g. And if you remember back to the video, then the derivative of the product is equal to the derivative of the first one times the second one plus the first one times the derivative of the second one. Right, so the derivative of this one by the power rule is just going to be 2x. Now, the derivative of g is actually, we have to do a bit more work here. It's a composite function. Right. And this is our f. Okay. So we're going to have to do the derivative of the outside function with respect to the inside function. And then the derivative of the inside, well, the inside function there, the derivative of that is just 5. That's fairly straightforward. So basically, we've got, well, we've multiplied the coefficient by the exponent, giving us a half, and then we've subtracted 1 from the exponent, giving us minus a half. All right, so the whole thing is, that's your f, that's your g, that's your f dash, your derivative of f, that's your g, that is your f, and this is your derivative of g, okay? And that bit is your df, dx, dg df, beg your pardon, that's your dg df there, and this is your df dx here. Right, okay, so we've got all this now. I won't go through the steps. Basically, we just have to do a bit of work on this to simplify this. You just have to kind of see where we want to end up. So we want to take, get 5x plus 2, I should, it's 5x plus 2, on the denominator. So basically, we do a bit of rearrangement and we get all that lot, and that tells us what our values of A, B, and C are. Okay, so that is that. Right. Of course, you can stop and uh, kind of rewind at any point and just check these or go over them again if you so wish. The equation of a curve is y equals x times the square root of 16 minus x squared over this domain. Find the exact coordinates of the stationary point of a curve. Exact means basically calculator decimals. We don't want to be doing that. Right, okay, so again, we're using the product rule. So that is the derivative of, so if this is our f and this is our g, then that's the derivative of f. This is g written in exponent form as opposed to like a square root, plus f times the derivative of g. Now, similar to the last one, we've basically got the chain rules. So this bit is our dgdf. Okay, and this is our df dx. Right. So again, we've got a combination of the product rule and the chain rule in one derivative. It's quite common, and if you get an exam question on that involves differentiation, highly likely that you're going to have to do this. Okay, so we can simplify that and um, end up with something like this. No, exactly this. Find the exact coordinates of the stationary point or turning point. And at that point, of course, then the gradient is going to be zero. So dy dx is equal to zero. So we can form the equation of this against zero and basically solve for that. And when we solve for that, so you can perhaps pause the video and go through the steps if you're not convinced or you want some more detail. We're going to get this x equals plus or minus 2 root 2. Yeah, we kind of expect it to be more than one solution there, wouldn't we? Right, so that's your x coordinate. It does actually say the coordinates, so we're looking for y. And so basically, the stationary point on the curve. So we've got so when we substitute y, I've substituted x, beg your pardon, in this function here. Well, I've got plus or minus 2 root 2. We're not kind of not going to all that, but essentially we're going to get y equals 8. So that is going to be our solution. All right. Okay. As we speak, was wondering whether or not we have got 2 points. I'm going to have to check that later. I'll put that on the description. Right. Find the equation of the tangent to the curve. There we got a cubic, a positive cubic. Positive cubics go like this, don't they? Something like that. Sometimes these 2 points here sort of come together. All right, so that's going to be the gradient function, as I call it, anyway, dy dx equals 3x squared minus 12x plus 3. And when x equals 1, that gradient actually, when we evaluate that, the gradient is minus 6. So the gradient is minus 6 when x equals 1 on this particular curve. Right, so that's going to be the gradient of the tangent at x equals 1. And if that's the case, then that tangent, which is a straight line, of course, is going to look like that. We don't know C yet. How do we find C? Well, we we can basically just work out a point on the line, well, the one to do is we know that it passes through the point where x equals 1. So let's find out the y coordinates of that as well, which turns out to be 8. That's as if we substitute 1 into there. So this curve, this cubic here, passes through the point x equals 1, y equals 8. Right, and if we substitute those values now into our into our sort of half-formed straight line, we're going to get value of c equals 14, which we can then pop back in there. So the equation of the tangent is going to be y equals minus 6x plus 14. Okay, so that is sort of turning point question, typical one. It is given that y equals a natural log of 1 plus sine x. Well, right, okay, we're sort of moving away now from algebraic functions, something a bit more exotic here. Find dy dx. All right, so again, using the chain rule, this one here is your f. So g is natural log of f is 1 plus sine x. And here we go. Here's the chain rule for differentiation. dg df. Right, okay, so this is one of the standard ones. Is going to be 1 over f, and f is 1 plus sine x, times df dx. That's the derivative of that. Df dx is, well, the constant goes. Derivative of sine x is cos x. That's what we got there. So essentially, it's just that. Okay. Not too difficult. A curve has equation y equals x cos x. Find dy dx. Right, so here we're going to use the product rule with f equals x and g equals cos x. Dy dx is, yeah, the same formula there. So that's the derivative of f. That's g. That's f. That's the derivative of g. So we rewrite as that. Okay. Right. Okay. We're blazing through these. Oh, right. This is where we slow down a bit. Find the equation of the tangent to the curve, that lot, at the point where x equals 1. Give your answer in this form. Yeah, it's the tangent, so it's going to be a straight line, isn't it? So in a particular form. So it basically means explicit in y. We just got y on its own on the left. Right, so we're going to use the quotient rule here. You know, that and that. And all right, so the derivative of the numerator. Right, okay, right, we're running into problems already because we've got composite function in the numerator. So this is another one where we've got, the chain rule nested inside the product rule. Inside the quotient rule in this case. I mean, we could have it the other way around, where the quotient rule is nested with inside a chain rule problem. All these things are potential types of problem. So we just have to look at what is the derivative of this numerator. So basically, what we've got is that. And f is equal to x equals 3x squared minus 1. So dg df is going to be equal to 1 over f. Remember that from the previous video. And the f dx is going to be equal to 6x. 1 over f, of course, is just 3x squared minus 1. Let's just change that, shall we? Just do it. Well, plane. 3x squared minus 1, if I can just get that working. And so dg dx is the product of these two things. So basically it is equal to 6x over 3x squared minus 1. Right. Which is what I've got there. Right. So as I say, we've got that is our um, F prime here. These are different these are different G's and F's while we're working out the that numerator. But in terms of the product rule, this is our F dash here. So, okay, so that's perhaps the difficult thing to get your brain around. And the trouble is we kind of use the same letters, don't we, for these things. So you have to be very ordered about how you do these things. Just make sure you know what sort of kind of work out, if you like, from the inside and build up your total derivative. So there's your F dash. Your G dash here, of course, is just one. And so we have, right, so this is um, F dash times G. F dash is going to be that bit, and that's your G, minus F times G dash. G dash, so it's 1. All divided by the square of G being the denominator. So that's what we've got. Right, so all that stuff. I mean, we could kind of rearrange that. In a way, we don't really need to because we just need to evaluate it at 1. So this notation here means we're going to evaluate it at x equals 1. So we substitute all that in there, and basically, what we get for the gradient of this tangent at x equals 1 is this number here. Right, as before, we know the gradient, but we don't know the constant c here, do we? So we need to know a point that this line goes through. We're obviously going to go for x equals 1. But we have to go back to the original function here in order to be able to find the value of y when x equals 1. So we just substitute 1 into that original function, and then that's going to give us that, which is equal to that. So we've got our gradient, we've got our intercept, so we can write the equation of the line using this little formula, y minus the y coordinate of the point that we're using equals the gradient times x, the general point, minus the x coordinate of the point that we're using, giving us that. Woo, that. Okay. All right, so that did take a bit longer, didn't it? All right. I see they're getting more complicated, these, aren't they? Variables x and y are such that y equals e to the power of x over 2 plus x cos 2x, where x is in radians. Use differentiation to find the approximate change in y as x increases from 1 to 1 plus h. Yeah, okay. So, this is just another way of asking you really what the derivative is at 1. If we know what the derivative is at 1, then an increase in h is just going to be that derivative, that gradient, times h. Yeah. Right, so what have we got? So when we look at these two, we can look at these two separately, obviously. Now here, it's sort of the chain rule here. Um, this is your inside function here. So when we differentiate, well, we differentiate we get the derivative of e with respect to the inside function, which is e to the power of x over 2. Because that's the rule, isn't it? For the derivative of that is equal to that. Yeah. Um, and then multiply by the derivative of the inside function, and the derivative of the inside function is going to be a half. So that is the half from your df dx, and this is your dg df. Right, so that's that bit. I mean, when if you do these all the time, you don't think of it like that, really. You've kind of automatically just think, okay, it's going to be half e to the power of x over 2. So you don't have to go through all that kind of thinking, really. It will just become a bit more automatic to you. And then, all right, we've got up to the product rule here, but not only we got the product rule, we've also, when you think about cos 2x, again, what we've got is cos of f, where f equals 2x. So we got that to do as well. So we apply our product rule, we got the derivative of the first function there times the second function. That's easy enough. And then we got the second function, x, times the derivative of the first function. Right, okay. So the derivative of the first function, so we got minus sine 2x times the derivative of the inside function there. And the inside function is this, which is 2. Okay. All right, so the minus comes from differentiating the cos, the 2 comes from there. Right, okay. You might want to stop the video and just convince yourself of that, but that's what we get. All right, and when we evaluate that at 1, again, we could probably find a way to simplify it, or maybe, I don't know. But all we have to do is plug 1 in for all these values of x in here, and when we do that and work it out, we get this value here. So what I was saying is that as x changes by h, well, any change is it's proportional to this, basically, isn't it? So a change in one would reduce your your y by this value here, but we're just changing it by h, so the y is going to change by that. Okay. So what that's kind of saying is that the change in y is going to be minus 1.41 h, 1.41 h, and the change in x is going to be h. It's gradient, of course. And that's the gradient. So we just kind of worked it backwards. Right. Okay. So move on now to now we have a sort of more practical problem. So this is another one that involves two variables. Um, so what we got? A container. Here's a circular cylinder open at one end with a base radius of r and a height of h. The volume of the container is 1,000. Given that r and h can vary, yeah, they're going to vary, but of course, if r gets smaller, then h has to get bigger, doesn't it? So they kind of vary, but they're varying together. So h and r are connected. So we could actually write h as a function of r, couldn't we? Yeah. So given that these can vary, and the total outer surface of the area of the container has a minimum value, find this value. Right. Okay, so um, well, Well, we know that the volume is, well, we know it's actually, the formula for it is pi r squared h, and that is, and the volume is 1,000. So actually there's our formula linking R and H. Yeah. As R gets bigger, H will have to get smaller, and vice versa. So that's what does that. So I'm going to write that in terms of explicit in H because I'm going to substitute for it in a minute. The surface area, well, the surface area we're talking about is not completely obvious from the question, basically, but it's the curve bit plus the bottom. Um, it's a container, isn't it? So you kind of expect that. All right, so that's going to be this. So 2 pi r h. That well, that's the circumference, isn't it? So the curved surface area is 2 pi r h. Yeah, multiply that circumference by the height. Yep. And then we've got the area of the base, which is pi r squared. All right, so that is the surface area. Well, let's get rid of h because we start to cause ourselves problems if we need to work in two variables basically. So if we substitute this h into here, then we're going to end up with this, which simplified. Well, there's going to be some cancellation here of pi and r. We're going to get to that. So that is the surface area. Okay, so right. Well, this is going to vary, isn't it? This is not a straight line. We've got a divided by r and an r squared here, so it is going to be some not simple curve, but we can find out where the turning points are. And um, so when we take the derivative ds we're going to get this function. And at the minimum value that we're trying to find, the dsdr is going to be 0. So in other words, this thing here is going to be 0. Okay. Oops, hang on a minute. This is going to be 0. All right. So just rewriting that, it gives us that, and therefore r cubed equals that. Dum dum dum. Yep. So that's our r cubed, and therefore at the minimum value we can substitute this. Well, it's the cube root. R is the r at the minimum value is going to be the cube root of 1,000 over pi. Yeah. And so we can substitute that into the equation for the function for s into there. Okay, on this side we've got a square there, haven't we? But then we've got the cube root to apply to this as well. So that's how it's going to work out. And we can work all that out, and it comes to this figure. So this is now what we haven't done is it basically kind of consider other turning points and whether or not we're doing it, whether it's a maximum or a minimum or whatever. But basically we're told there's a minimum value, so we don't really have to do any more work. We found the minimum value and we can just plug it in there, so we're not going to worry about that. Little graph here just to help illustrate. So this is at this portion of the curve. I mean, we'll find where this thing is probably got turning point when for negative on the horizontal axis, which is not going to be part of the solution because the radius obviously has to be positive. Okay, so there we go. There is a turning point. Is that the yeah, that it's round about there. Those numbers don't actually come into it. We don't need them. But yeah, so that's what it's going to look like. Oh yeah, sorry, 439. That's right. That is the value on the vertical axis. In other words, the surface area. at the minimum. Right. And this is going to be the cube root of 1,000 over pi, there, 6.82, etc. Right, okay. Do we have any left? Yeah, we're almost there. Find the x-coordinates of the stationary points of the curve there. Uh, this is very similar to what we've just done elsewhere, where really. Derivative of that is that, for the reasons I said before, and the derivative of that is going to be that's your dgdf, and that's your df dx. So the derivative of this bit is going to be that. Right. So now we know that, then we can apply the product rule to that. Yeah, so we know the derivative of that, and we know the derivative of that. So we can just plug those into the product rule. And when we do that, we get that, and it simplifies down to this. Now, there is one good learning point from this. So at the stationary points, then all that lot is equal to zero. That's your derivative there is equal to zero. But the thing to note here, I mean, what we say, we've got products of things that equal zero, then one of them has to be zero. Okay. Well, we know that this one isn't. Exponential functions where, the base is a positive number, are always going to be positive, regardless of the value of x. So that doesn't kind of come into it. So either this is zero or this is zero. And yeah, that's straightforward. But for this to be zero, then obviously 2x plus 3 has to be zero. So that's going to give rise to this solution, this to this solution. So those are your two points, or the x coordinates of the 2 points for the stationary points on this curve. All right. So this function looks a little bit nasty, doesn't it? But so if we do it sort of, we kind of build it up, by finding the derivative of that we can then use in the product rule. Yeah, and that's the kind of way to do it. I think this is the last one here. A curve has equation y equals f of x, and so exactly 2 stationary points. Given that the second derivative is 4x minus 7, and the first derivative at 0.5 equals 0, and the second derivative at 3 equals 0. In other words, x equals 0.5 and x equals 3 are both turning points. Use the second derivative test to determine the nature of each of these stationary points on the curve. Right. Okay, so we're given the points, and we know that they're turning points. So if we evaluate the second derivative at these points in turn, then we can note the sign, and that will tell us whether or not it's a maximum or a minimum. Okay, so looking at 0.5, if we substitute that into the second derivative, we're going to get 4 times 0.5 minus 7 equals minus 5. That's going to be a maximum. That's your situation. And then for when x equals 3, then we're going to get 4 times 3 minus 7 is equal to plus 5, and that's going to be a maximum. Right. Okay, so a bit of a marathon going through all those. Thank you very much to Save My Exams for providing those questions. Um, so I hope you have found that useful. So I think, I mean, some of the more complicated and sort of high tariff exam questions, basically saving those for another video. These are the more sort of mostly the more mechanical one. Although we have had the volumes of cylinders. Those are a little bit more difficult. But if you can understand the first video and then understand these work solutions in this work solutions video, then you're going to be pretty proficient at differentiation. Um, of course, differentiation is a tool that we use in the whole of calculus. So you're not going to run out of things to do in calculus. So don't worry about that. Okay, well, that's it, and thanks for listening.